In today's video, we're going to be covering section 2.4, the inverse of a square matrix. What I want to look at in this section is exactly what is the inverse of a matrix, what does it look like, how do we find it in certain cases. We're only actually going to be doing it by hand in this section for a 2 by 2 square matrix. For matrices larger than that, we're going to look at a way of doing that in 2.5, or you can use a calculator. So I'll also go through that as well. But the main thing that I want to look at in this section is what is the inverse, what is it used for, and how can I find it for smaller matrices. So first of all, what is the definition of the inverse of a matrix? The inverse, and always bear in mind, I'm only looking at square matrices. You cannot find the inverse of a matrix if it is not square. So the inverse of a square matrix, we're going to call it n by n. So it has n rows and n columns. So the inverse of a matrix A is given by this matrix A inverse, such that these two properties hold true. Okay. So when I multiply A by A inverse on either the left or the right, because remember from our matrix multiplication discussion in section 2.3, we know that we don't always get the same matrix back when we multiply a matrix by another matrix on the left and the right. So we get different resulting matrices as we are multiplying different rows and columns, and sometimes that multiplication can be undefined. But in this case, I get the same matrix back regardless of which way I multiply them, and I always get that square identity matrix back, that n by n identity matrix, as my solution regardless of which way around I multiply these two matrices. If you think about it, it's kind of like a matrix analog to fractions when we look at scalars. So for example, if instead of looking at matrices, if I look at numbers, so if I took the number 2, if I multiply it by 1/2, I get 1, and it doesn't matter which way around I multiply 2 and 1/2 in, like which order I multiply them in, it doesn't matter. I still get that multiplication identity back, that number 1, and in the matrix form, I get that identity matrix. So a matrix inverse is effectively doing that same kind of thing that a fraction would do to a scalar when we look at standard multiplication. Why are these inverses useful? When am I going to use this? I want to take you back to what we did with our systems of equations, where I said that whenever you have one of these systems, we looked at this in 2.3, I can write this as A times X is equal to B. So I'm going to give you just a system of equations here so that we can write this out. And negative 3x plus 7y, I'm going to say is equal to negative 6. So we've got these two random equations. I want to solve them simultaneously. Now we said in 2.3, I'm going to rewrite this as a coefficient matrix multiplied by a column matrix equal to this other column matrix. So A times X is equal to B. Okay. And we said just by multiplying this back out, I would end up with my system of equations. It was just another way of writing this system of equations. If your system has a unique solution, and we will look at that in a second, if your system has a unique solution, you should be able to find this A inverse matrix And by using it, I can easily find what this unique solution to my equation is. I can find out what this matrix X is, what my X and Y variables are. All I have to do is multiply both sides of my equation by that matrix A inverse. Okay, I've just multiplied both sides through by A inverse. By doing that, if I go back to my definition here, A inverse multiplied by A is just the identity matrix. So I can simplify what I have here by saying that A inverse times A, which I have here, is just the n by n identity matrix multiplied by X equal to A inverse times B. Now we know from 2.3 that our identity matrix multiplied by any matrix, as long as your dimensions match in order to do the multiplication, just equals whatever matrix I have. So here, the identity matrix times X. Well, X has n variables in it. Okay, if we come back to our example here, this IN would be I2. It would be the 2 by 2 identity matrix multiplied by a column matrix that has 2 entries in it. So I know I can go ahead and do that multiplication. So if I do the identity times X, I just end up with X by the properties of that identity matrix. And that simplifies to X is equal to A inverse times B. This gives me another way to find my column matrix X. Okay, all I have to do is find that inverse matrix of A, that A inverse matrix, and multiply it by my column matrix B, and I get what my X and Y are in my example here. Or if you have more variables, it would give you the value of each of them for that particular system of equations. So it gives me another way to find my unknown variables. Like I said, this works if you have a unique solution. It only works if you have a unique solution. So that takes us back to the examples that we did in 2.1, where there was exactly one solution. So each of your variables only had one possible number that they could be. Okay, it wasn't like we had in 2.2 where we had no solution or infinitely many solutions. It doesn't work in that case. It turns out that you can only find A inverse if you have a unique solution to your system of equations. So you would actually find that you come across an issue finding A inverse if it turns out that your system of equations doesn't have a solution. So it actually helps you out there that you know that you're going to come across one of our problems from 2.2 where we had no solutions or infinitely many solutions if A inverse cannot be found, if you come across a problem when finding A inverse. So the question is, how do we find it? And like I said, we're going to do this with a method by hand for 2 by 2 matrices. For larger matrices, we will look at that in the next section, and you can also go ahead and use a calculator, especially for the larger matrices. So we're going to look at inverses of 2 by 2 matrices. So let's say I've got a matrix A is a 2 by 2 matrix. So I'm just going to put in A, B, C, and D as whatever my values are in my entries in my matrix. Okay. I'm going to define this value D. And D is going to be defined as A, D minus B, C. Okay. This value, and we will come across it again, it's actually called the determinant of a matrix. So I'm going to let D equal to that value. Then A inverse is defined as 1 divided by that value D. And then I'm going to switch my positions of A and D in my matrix, and I'm going to make B and C negative. So let's look at what we've done here. A is this 2 by 2 matrix with values A, B, C, and D in my entries. I've defined the determinant of a matrix as A times D minus B times C. Then to find A inverse, I do 1 divided by that value, whatever A, D, and B, C are. You can go ahead and find that value D. And then 1 divided by D multiplied by this matrix where I've switched where A and D are from my original matrix. And whatever B and C were, I've made them the negatives of what they were. So I changed the signs of B and C in my matrix, and that gives me A inverse. If you were to do the algebra, you should find, just by multiplying all of this out, so multiplying out your rows and columns, etc., like you do with matrix multiplication, you should find that A times A inverse equals the 2 by 2 identity matrix, and similarly the other way around should also equal the 2 by 2 identity matrix. So I encourage you to go ahead and do that at home and figure that out just by multiplying this out algebraically for these 2 by 2 matrices, just by multiplying out the rows and columns using these values A, B, C, and D, and you can see that you should get 1, 0, 0, 1 as your matrix that comes back out. I'm going to do a quick example of this so that you can see this in action. So we're going to find the inverse of this matrix, -2, 4, -3, 7. So it's the matrix that we had from earlier, that coefficient matrix. So first thing we do is we find that determinant value, A, D minus B, C. So that would be -2 multiplied by 7, because I've got A, B, C, and D. So -2 multiplied by 7 would give me -14. And then B times C would be -12, but we're subtracting it. So it's going to be plus 12, and that gives me -2. Okay. So my determinant value is -2. Then to find A inverse, it's 1 divided by D multiplied by this matrix. I need to switch the positions of A and D. So 7 now becomes my top left element, and -2 goes in the bottom right. And B and C become the negative of what they were, but stay in the same positions. So if you multiply this out, this fraction here, 1 divided by -2, is -1/2. You can pull that negative out the front here. Okay, so you've got -1/2. Okay. So your matrix now becomes -7/2, and then I've got -1/2 multiplied by -4. So the negatives cancel out, and I get 4/2, which is just 2. Then I get -3/2, and then -1/2 multiplied by -2, the negatives cancel out. I get 2 divided by 2, which gives me 1. Okay. Now, you can go ahead, I will do this one way just so that we've got it, but you can go ahead and multiply A by A inverse, and similarly A inverse by A, and you should still get that 2 by 2 identity matrix as your solution when you multiply them. So if we go ahead and do -2, 4, -3, 7, multiplied by -7/2, 2, -3/2, 1. Okay. I'll do A times A inverse, and you can go ahead and do A inverse times A to prove the point. But we're going to do row times column. So that's going to give me 7 minus 6, which is going to give me 1. And then row times column is going to give me -4 plus 4 is 0. Then we've exhausted the columns in the second matrix, so we move to our next row. So row times column. That will give me 21 over 2 minus 21 over 2, which is 0. And then I get negative 6 plus 7 gives me 1. So I get the identity matrix back. So here we have done A times A inverse. Now you can go ahead and do A inverse times A, and you should also get the 2 by 2 identity matrix out, showing that this matrix A inverse is actually our inverse of A. So it's pretty simple to do once you know what the formula is to find A inverse. So now you can go ahead and use that inverse matrix A to go ahead and help us whenever we try to find the solution to these systems of equations that we have been looking at. A times x is equal to b. Okay, so remember we had our systems of equations. We could go ahead and write them in this matrix form like we did in 2.3. And now we can use that inverse matrix if there is a unique solution to find what that X matrix is, that column matrix. So this is if X has a unique solution. So like we had in 2.1. How will we know that it has a unique solution? Well, it comes back to our determinant value that we had here. Okay. When you find that determinant, it has to be non-zero. I'm going to add this into our description when we found the inverse of a 2 by 2 matrix. That value has to be non-zero. Otherwise, you come across a problem here where you are dividing by 0. You can't divide by 0 in math. It's undefined. So when you come across these inverse matrices, you're going through the process of finding the inverse. First thing you do is find that determinant. If it equals 0, you know that A inverse cannot be found. Therefore, coming back to our systems of equations here, that tells me that this system will not have a unique solution because I cannot find A inverse in that case. So whenever you do one of these problems, first thing you do is find the determinant. It should be non-zero. If it is non-zero, you can go ahead and find A inverse, and then all you would have to do is multiply it by that column matrix B, whatever your right-hand side is for your system of equations, and that will give you your unique solution X. If you come across the problem where that determinant is 0, so you calculate AD minus BC and you get 0 back, that tells me that I cannot find an inverse for A because I can't divide by 0. So the inverse for A cannot be found, and therefore this system of equations will not have a unique solution because I cannot find X that way. Okay. So whenever you do this, just look at the determinant value first. Okay, so we have to look at AD minus BC to see if it equals 0 or not first. If it does equal 0, A inverse doesn't exist. If it doesn't equal 0, we can go ahead and find A inverse, and hence we can find a unique solution for our system of equations. So if we come back to our problem that we had here, our initial system of equations, my right-hand side matrix was 7, negative 6. So I found my inverse for A, which was this matrix here. If I were to multiply this by 7 negative 6, I would then get my solution x. So if we multiply these two together to find x by using our row, dot product with the column, etc., you should find that x is equal to negative 73 over 2 and negative 33 over 2. So this would be our x value and this would be our y value for that given system that we had before. So and finding A inverse is very, very useful in these situations. I'm going to go ahead and do this now on the calculator. Obviously, and we'll look at this in the next section, you can find the inverse of a larger square matrix. So I could easily do A is equal to some 3 by 3 matrix, plug it into my calculator and find A inverse. We just cannot find A inverse this way for anything other than a 2 by 2 matrix. We would have to use a different system by hand in order to do that for larger matrices, and it can get complicated using a formula like we have here to find A inverse. So in the next section, we're going to look at how we can actually find the inverse matrix for these larger square matrices, or we can just do it on the calculator like I'm going to do now. So what I'm going to do here is I'm going to go into my matrix menu like before, and I'm going to edit my matrix A. And you'll see here, I've put it as the 2 by 2 matrix that we were finding the inverse of earlier. So this was my matrix A. So I've put it as a 2 by 2 and plugged it in as a square matrix. Then if I come out of the matrix menu, so I do second and quit, I'm then going to go back in and call that matrix. So go back into the matrix menu, click enter, and now I want the inverse of the matrix. So I'm going to click this inverse button here. So it looks like A inverse. Click enter and you will get that exact inverse matrix that we had earlier. So you're just going to call the matrix and then put the inverse after it, and that will give you the inverse of that matrix. If you want to find that matrix X, that solution to that system of equations that we had, all you have to do is in your calculator type A inverse B, and that will give you that exact same vector that we had before, that column matrix that gave me all of my variables. So again, if I go back into my matrix menu and I'm now going to edit B, and you'll see I have made it a 2 by 1, and I've made it exactly what we had for my right hand side of my system of equations. So I've got 7 and negative 6. Now if I come back out of my matrix menu and go back in, I'm going to call A inverse, and then I'm going to multiply that by the matrix B. So I'm then going to call the matrix B right after it. Click enter and you will get exactly what we had. This is in decimal format. We put it in fraction format, but it is the exact same answer. So this is a great way to check your solution if you do these by hand.